So in the previous video, we saw the unit tangent vector to a space curve at a point. Now today let's go back to that idea and briefly see what it was, because still there is something else we need to see about it. So let this C be your space curve, which of course does not look like a general space curve because we have drawn it on the plane of this whiteboard, but you understand that it can twist and bend in space in any manner. And its equation is given by this vector function r of alpha, where alpha is a parameter that varies over some interval of the system of real numbers. And the setup is such that as alpha increases in that interval, r of alpha also likely changes, which is the vector, and that is the position vector of a point on the curve, which also changes, and accordingly the point also changes, and in doing so the point traces the curve. It draws the curve in space. So there is a direction in which that happens, and that direction corresponds with the direction in which alpha increases in that interval, which is there in the background. Position vector with respect to what? With respect to some fixed point as the origin. Okay, so for example, a typical point A on the curve is this. So for some specific value of alpha in that interval, whatever it is in the background, this is the position vector of the point A with respect to the origin O. Okay, so that's the space curve. And the unit tangent vector T of alpha for that specific value of alpha at this point A to this curve is by definition this. The derivative of r with respect to alpha at that specific point alpha, and this is the vector which we divide by its magnitude, obtaining a unit vector. So there are two conditions that must be satisfied here. The first thing is that the function has to be differentiable at that value of alpha so that the numerator vector exists, and the denominator scalar should be non-zero, and for that the numerator vector should itself be not the zero vector. Alright, so this was the general setup. Now today what we are going to see first is we will take a specific parameter in place of alpha, arc length as measured along the curve. And if we take that specific parameter, then this denominator becomes 1. Let's see how. Let's see that first, and then we will go to unit normal vectors. Suppose this is a fixed point on the curve from where we are going to measure length, arc length along the curve, and we denote that arc length by small s. Accordingly, every alpha has changed to s. For some specific value of s, which is say this much, we get the point A. And of course, r of s, again the same thing, is the position vector of A with respect to O. The only thing now is that alpha is s. So A is some point on the curve. It has the position vector r of s, and say B is a nearby point, which corresponds to this s plus delta s. Delta s is some increment in s. Note one thing carefully, that s is positive. It can be 0 also if your point lies here. S is not negative, but delta s may be negative, because delta s by definition is a difference of two values of s. That can be negative depending on the situation. Here, however, delta s is positive, suppose. So this much is s, this much is delta s, and this is the point B with this position vector with respect to this point O as the origin. Alright. Now what is this delta r? This also we already know. This delta r is this vector minus this vector, this. And note carefully that this the length of this curved part is delta s. Alright. Now suppose that the unit tangent vector to to this curve at the point A exists. That means this exists is a non-zero vector. So you can divide by its magnitude, all those things are there. Now we claim that this denominator is 1. Let's see how. So we take the denominator, the magnitude of dr ds. Now dr ds by definition is of course this limit as delta s approaches 0. And here I am not saying that delta s is positive, okay. You just forget about this figure for a moment. Here delta s can be positive, I mean it is both positive as well as negative. Both the cases are there in this two-sided limit. Because it is two-sided limit, delta s will approach 0 from the right side, in that case it is positive, and also from the left side, in that case it is negative. Of what? Limit of what? Limit of delta r divided by delta s. But if this limit exists, we are saying that the derivative exists, which means that this limit exists. Then the right hand limit also exists and is equal to this limit. So that is why the magnitude of this is equal to the magnitude of this. This is the right hand limit. And now we can consider this figure where delta s is positive, and in this one-sided limit, right hand limit, delta s really is positive. Okay, but then what is next? So then we have this. The magnitude goes inside the limit. To see how you express this vector, not the limit, okay, only this vector as a linear combination of I hat, j hat and k hat, those orthogonal unit vectors. And then from there you will get this. I won't say anything more about that, okay, it is something very easy. So we just accept that this happens, and now we have the limit of the magnitude of this vector. Now if we look at this vector, it's actually a scalar multiple of the vector delta r, where the scalar by which we are multiplying that vector is the reciprocal of delta s. Delta s is a positive real number. And from the definition of scalar multiples of vectors, if you go back and see the definition, the magnitude of such a scalar multiple is the magnitude of the original vector multiplied by the absolute value of the scalar by which you are multiplying. In this case, that scalar is 1 divided by delta s, because delta s is positive due to us considering right hand limit. So the absolute value of 1 divided by delta s is just 1 divided by delta s. Okay. And now you see this figure. What is the magnitude of delta r? The length of this line segment. And delta s is the length of this curved line. Now as delta s becomes smaller and smaller, the point B approaches A, and in the limiting case, this and this become the same. And that is why this entire limit becomes 1. So that's how we find that this magnitude is 1. So then what are we getting from this? This is what we get. The unit tangent vector, if the parameter is arc length along the curve, is dr ds itself, the derivative itself. That's because the magnitude is 1. And now using this fact that this t of s is a unit vector, we are going to see how we can get the unit normal vector from that. Unit normal vector. So just now we have seen that this t of s is a unit vector. So if I take the scalar product of it with itself, then I will get the scalar 1, that means the real number 1. Or if I write it more simply, it looks like this, t dot t is 1. Now t being a function of s itself, it can be differentiated once more with respect to s. I mean this itself is a derivative, we can differentiate once more. And actually we are going to do that to this equation. And then let's see what we get. So we do the differentiation. The left hand side becomes dds of t dot t, and the right hand side becomes 0 because it's a constant. That thing still remains. Whether you are dealing with scalars or vectors, it does not matter. If something is constant, its derivative is 0. With respect to the independent variable, of course. So then you recall one of the properties of derivatives of vector functions, which involves scalar product. So this equals dt ds dot t. I mean, we differentiate one of the vectors at a time, keeping the other one intact. We don't touch that. So here say we differentiate this one and keep this one intact. That way we get this, plus then we keep this one and differentiate this. In this case both are the same. So that way you get this equal to 0. But we know that scalar product is commutative. So dt ds dot t and t dot dt ds are the same thing. So we get 2 times dt ds dot t equal to 0. And then of course this just means that this scalar, it's a scalar, okay, because this is scalar product, this is a real number. 2 times this is 0, so this must be 0 because 2 is not 0. So you find that this other vector, it is something, dt ds is perpendicular to the unit tangent vector t because the scalar product is 0. So we write like this, so dt ds and t are perpendicular to each other. Now we can write the vector dt ds as its magnitude times some unit vector which points in the same direction as the original vector. Say the magnitude is this Greek letter kappa times n hat. This n hat is some unit vector which points in the same direction as this vector dt ds. And we write that also to make it more clear, where kappa is the magnitude of this vector. This kappa has a name also. It's called the curvature of the curve C at the point S. Well, does not look like kappa depends on S, but of course it depends on S. For ease of writing, we dropped S from the notation of T, right? We simply wrote T overhead arrow, but actually it's a function of S. In fact, that's why we are able to differentiate it with respect to S. So as S changes, this dt ds also changes. I mean, it's the function of S itself, and accordingly this magnitude kappa is also a function of S, a scalar function or an ordinary real valued function of S. So that's how it is called the curvature of C at S. Just like that, this other vector which comes with it, which is the unit vector part n hat, also is the function of S, and that n hat is called the principal unit normal vector to C at S. Note that just like the unit tangent vector is perpendicular to this, it will also be perpendicular to n hat because n hat is parallel to this and also points in the same direction as this vector. So as your S changes, okay, in whatever interval it changes, which is there in the background, that point A moves on the curve, and with A, the unit tangent vector T also likely changes depending on how the curve is twisting and bending, or whether it does not twist at all. And with that, the unit normal vector, which is perpendicular to the tangent, also changes. Okay, so that these things maintain the fact that they are perpendicular to each other, no matter where the point A is on the curve. And there is one more thing which the author did not immediately mention in the text, but he mentioned in one of the examples, is that just like kappa is called the curvature of C at S, its reciprocal is called the radius of curvature. Now let's go back to that example which we saw when we discussed unit tangent vector, and in that example, that cycloid I think it was. In that example, let's now calculate unit normal vector. Example 1, 2. So not exactly the same example as that one, but the curve is the same. So now we have to find the unit normal vector and curvature of the cycloid. Cycloid is the same. X equals a times theta minus sine theta, y equals a times 1 minus cos theta, and z is equal to 0. So these are the coordinates of any general point on the cycloid. And you already, I think, you can remember the figure. It was like this. and A is positive, not mentioning that again, where theta lies between 0 and 2 pi in this manner. Now we are going to use something we have already calculated in that example, namely the unit tangent vector. There you go back to the previous video, there you will see that the unit tangent vector t at theta, note one more thing carefully, this is theta not s, so we have to do something about that also. But anyway, t of theta is sine of theta divided by 2 I hat plus cos theta divided by 2 j hat, where I hat and j hat are unit vectors in the positive directions of the x and y axis respectively. So we then straight away go for dt ds by the chain rule that equals dt d theta divided by ds d theta. Chain rule is available for vector functions as well. And then this equals the magnitude of dr d theta. How and what is this r? This r is actually that vector function which you get from the given x, y and z as their linear combination using the vectors I hat, j hat and k hat. It is that r which we used in the previous example, from where we found that t of theta. Okay, so it is that r. But why is this equal to this? To understand why, you go to the figure that we saw today and you analyze how we have dr ds equal to 1. You just see that from there this is coming. But anyway, there is no absolute need for you to know everything mathematically about these things, because anyway we are not going to study the mathematics here, but rather we will use these things in doing physics. So that's why we don't go too deep into these things. We just accept that this is equal to this. Now this is also something we calculated in that previous example. From there we just use the value, it is 2s sine theta divided by 2. And what is dt d theta? That you can calculate from here itself, because your I hat and j hat, again, you recall that in that example we discussed the fact that I hat and j hat do not change. So when you differentiate this with respect to theta, you need to only differentiate the coefficients or the scalars. So you differentiate this, you get 1 divided by 2 times cos theta divided by 2, and you differentiate this, you get minus, because there is cos, minus 1 over 2 sin theta divided by 2. Okay, so now your dt ds looks like this. What are you going to get from this? You can simplify this slightly and write it like this. This 2 goes down means it's already down and gets multiplied with this 2, and in the denominator you have 4a times sin theta divided by 2. So I have written its reciprocal, times cos theta over 2 I hat minus sin theta over 2 j hat. Now note carefully that this is a unit vector, because if you take the sum of the squares of this and this, you get 1. Or in other words, if you take the scalar product of this with itself, you get 1. So this is that n hat, your unit normal vector to that cycloid at the point theta. I mean not at the point theta, that does not really make sense, at that point on the cycloid which corresponds to some theta value. And this is your curvature. If you take its reciprocal, what do you get? 4s sin theta divided by 2. That is the radius of curvature of the cycloid. Now after this also there is a small discussion in the text about why we call that quantity curvature and why its reciprocal is called the radius of curvature, and some other things, 1 or 2 more things, which we are going to skip totally, because this much differential geometry is enough for us right now. And the section ends here. And then there are exercises, which however we are going to entirely skip, because these are mathematical exercises. We won't do these things. Instead, in the next mechanics video, I will straight away start the next chapter, which is about velocity, acceleration and scalar angular velocity. So their mechanics really starts.